Engineering modernized by moving from paper drafting to computer-aided design, or CAD. A CAD model looks three-dimensional, but it remains strictly geometric. It is a visual representation of shapes on a screen, rather than a simulation of physical reality. In traditional CAD software, a shape has no intrinsic properties. The computer cannot differentiate between a heavy concrete beam and a hollow plastic pipe. To the software, these are different polygons. This created a digital environment where a building's physical intelligence, its materials and physics, was missing. When architects, structural engineers, and mechanical contractors generate isolated CAD drawings for a single project, the lack of data causes coordination to break down. Teams try to overlay these fragmented models to check for spatial conflicts, but the software often fails to recognize when physical systems improperly intersect. A ventilation shaft can clip through a load-bearing support without the computer flagging the error. These undiscovered digital clashes lead to stalled timelines and physical rework on the site. If a digital line crosses another unnoticed, the result is waste. To construct complex modern structures, the industry requires models that are self-aware and rich with data. Building Information Modeling, or BIM, addresses this by turning the spatial map into a relational database. Instead of an empty box, a designer creates a BIM object with mandatory parameters. The model tracks the element's specific type, material makeup, unique ID, and dimensions. We measure the reliability of this data using the Level of Development, or LOD, specification. At LOD 100, the object is a generic spatial placeholder. Compare that to LOD 400. At this stage, the model contains the precise structural mechanics and connection details needed for fabrication. For the crews on the ground, high-fidelity visual detail is secondary to the absolute reliability of this embedded data. Once the data is reliable, we can expand into the fourth dimension. 4D BIM links the intelligent 3D model directly to a project timeschedule. This allows teams to simulate the construction sequence in real time. By rehearsing the build digitally, they can resolve logistical bottlenecks before heavy machinery arrives on site. When we extract this sequential data to run quantity takeoffs, we generate a dynamic cost graph. This is the fifth dimension, cost and resource planning. This 5D data enables precise off-site fabrication. Digital components are serialized and manufactured in a factory according to the exact schedule of the virtual model. The addition of time and cost data turns the digital model into a predictive engine for the entire construction process. 6D BIM shifts the focus to post-construction operations and lifecycle facility management. Maintenance manuals, equipment warranties, and safety compliance data are permanently embedded within the digital twin of each physical element. The digital twin remains an interactive operating manual for facility managers throughout the life of the building. The industry is moving toward a unified, federated model, a single source of truth used by every stakeholder on a project. Managing this model requires architects, contractors, and owners to legally align their workflows through a BIM execution plan. This collaborative framework is known as Integrated Digital Delivery, or IDD, where data and risks are shared across the value chain. This technology supports a specific operational philosophy: build twice. First virtual, then real. By adopting multi-dimensional BIM, firms simulate a structure's entire life cycle, exposing conflicts and logistical risks before they can manifest on the physical site.